Welcome back to Algorithms and Uncertainty. Last time we started talking about online learning in worst-case models, and I've tried to summarize what we found out last time, or more precisely, what will be important for what we're doing today. So let's recap this. We have N actions, or as we call them in this setting, experts. And now we have an adversary who defines cost vectors L1 through L capital T. Lit, this is a number between 0 and 1, which is the cost of action I in step T. And now we'll have these capital T steps, and each of these steps looks as follows. Our algorithm chooses one of the N actions. Usually the algorithm will do this in a randomized way. Then the algorithm incurs cost, which is exactly the cost of the action that the algorithm chose in this particular step. And then it gets to know the entire cost vector. And based on this cost vector, it can change the decision for the future, or it can now adapt the probabilities, as we've seen, for future choices. And for this, we've got to know this multiplicative weights algorithm. Interestingly enough, for what we're doing today, it doesn't matter what this algorithm looks like. The only thing that matters is the guarantee that we derived. Namely, we derived that the expected cost that the algorithm incurs is at most this much. Eta, this was a parameter of the algorithm, and we showed that this is at most 1 plus eta times the minimum cost of any action throughout the sequence, taking the sum over all timestamps, plus ln n over eta. So what does this mean? This means now we are comparing ourselves not to the best action sequence, but we compare ourselves to the best way of choosing just a single action throughout the entire sequence. This is the minimum of all I, what is the sum of the costs of this particular action. So in this sense, it is somehow different from, say, a competitive analysis where we would take something like an offline optimum and where we might change our decision in every time step. And now we say, okay, in step 1, I take action 5. In step 2, I take action 3, and so on. So something like an offline optimum. Here, this is something weaker. This is just the best single action. However, this was well motivated by what we introduced, namely that we had this classification problem where, for example, we wanted to be as good as the best of our classifiers. And this is generally what we're also doing here. We want to be as good as the best action that we find here. And this is something that we can actually guarantee, namely this eta. This is a parameter of our algorithm, as I was saying. And if we set it to this quantity, namely the square root of ln n over t, then what we saw is that the expected cost of our algorithm is at most the cost of the best expert, the best action, plus something, and the something, this grows sublinearly in capital T, in the number of rounds. And this quantity we called the regret of our algorithm. So the difference between what cost our algorithm incurs and the cost of the best single action, this is what we call the external regret of our algorithm. And in the case of multiplicative weights, we'll get with an appropriate choice of eta, we'll get that the regret is bounded by 2 times square root t times ln n. And this now means that if the sequence gets large, if the sequence gets long, then this will grow probably much less than what these things grow. Okay, of course, it might be that after some point actions have zero costs, in which case this is not quite true, but generally speaking, we hope that every action, or that these things, just if they grow linearly, which is typical for what you'll see, then this term here will get negligible, which means that if the average cost of an action, or of the best action, is constant, then as t grows large, we get that our expected cost per time step will be this average cost of this best action. Good. So, what do we want to do today? Today, we will be talking about the exact same problem, but we'll modify the feedback a bit. Namely, this was again the setting that we had. So we have the adversary fixing the cost vectors. There's the cost of every action in a time step. And then, and this is what we're going to change, first the algorithm chooses an action in a time step. And then it incurs some cost. This is, of course, the cost of this particular action in this time step. And then it gets to know the entire cost vector. This is what we did so far. Now, there's actually only a very tiny thing that I have to change to make this a very interesting setting. Namely, we change the feedback to only the feedback of the action that we chose. So, before we said, okay, we get to know the entire cost vector. Now we say, okay, we only get to know the cost that we are incurring by the action that we're choosing. We don't get to know the cost of the other actions. And the rest just remains exactly the same. So again, we have this adversary defining these cost vectors. And also we are still interested in the regret. This is of course still all well defined. The only thing that is changing is the feedback that we're getting. And this is called partial feedback, or also the setting is called Adversarial Multi-Armed Bandits. And I hope you remember that we talked about this stochastic multi-armed bandit setting before, where we had, for example, this UCB1 algorithm, where we had the choice between different arms of our multi-armed bandit, and we wanted to figure out which of these arms is actually the best one to keep playing. But there, the rewards were determined by probability distributions. Now here, two things are different. The one thing is that instead of rewards, we're talking about costs here. This is actually only a minor change. This is only a flip in the sign that, in this case, doesn't actually make any huge difference. But what is actually different is that now we have an adversary defining all these cost vectors. So this makes this problem fundamentally different, because before, well, nature was at least not playing against us. We just could try to play some of these actions and then maybe figure out which of these actions or these arms turns out to be good in terms of the rewards that we're seeing. Now, this is a little more complicated, because what we're seeing in one step might be different from what we're seeing in another step. So why does actually the feedback for one step help us for what we're seeing in another step? That's not really clear. But what comes to our rescue is actually that still our benchmark will be the best single action. So it's not that we're comparing ourselves to the best action sequence, as I was saying, but that benchmark will still be the same, namely the best single action. Good. So This is exactly the problem that we'll be talking about. And what is interesting is that, well, I hope that first of all, this is a meaningful setting, because there are real life settings in which we will only get to know the cost of the actions that we choose and not the cost of the actions that we don't choose. But the approach via this multiplicative weights algorithm, this will turn out to be also applicable here. And it's even better than this. We will be able to show a black box reduction just taking any no-regret algorithm for the full feedback setting, where we get to know the entire cost vector, and we'll be able to turn this into a no-regret algorithm for this setting, where we get to know only the cost of the action that we chose. We will be deriving a black box transformation, which turns every no-regret algorithm for the full feedback setting into a no-regret algorithm for this partial feedback setting, or this bandit setting, as it is also called. So people usually call the full feedback setting also the expert setting, and the setting that we're talking about today, where you only get to know the cost of the action that you chose, this is what they also call the bandit setting, or bandit feedback. Good. How can we do this? What can we do with an algorithm for the full feedback setting? Well, there is a very simple but ingenious way what you can do. Namely, what we'll do is we will run an experts algorithm. And we'll now have PIT as the probability that the experts algorithm chooses expert I or action I in step T. Now, of course, to do this, we would not tell the algorithm, so that this works now, we would like to tell this experts algorithm what's the cost of every action that you can choose. But this is something that we don't know. We only get to know the cost of the one action that we actually then decide to choose. And what we'll do is we'll try to return the following. We'll try to return lit tilde to the algorithm as feedback. And this lit tilde is now defined as follows. We'll set lit tilde to be equal to lit divided by pit if I is equal to it, and 0 otherwise. So this is something that we can do in principle, because this lit, we know if this is the action that we're choosing, and 0 we can also choose. So this is generally something that we're allowed to do, because those are all things that we know. We know this lit, we know this pit of the action that we're playing, and we also can just set this to 0 for every other action. And why is this a good idea? Or why does this seem to be a good idea? This unfortunately doesn't work immediately, but what's the general spirit? The general spirit is that what's the expectation of this lit tilde? It is the probability that we choose action I times lit divided by pit plus, of course, the probability that we choose some other action times 0. Now what's the probability that we choose this as our action? This is exactly PIT. So this now nicely cancels and we see, okay, the expectation of LIT tilde is exactly LIT. So, in other words, or in statistical terms, this LIT tilde is an unbiased estimator of LIT. And if we are now feeding this back to the algorithm, this sounds like a very good idea. Because this is something that we know, and let's hope that the algorithm can work with this, what is only good in expectation. Well, unfortunately, it's not quite as easy. And what's the big problem about this approach? Well, we were assuming that the costs for the experts algorithm are somewhere between 0 and 1. Same thing as now, of course, for the LIT. Those are between 0 and 1. But LIT divided by PIT, this is by no means between 0 and 1, because PIT is also somewhere between 0 and 1, but this might be now huge. For example, PIT might be something like 0 or so, in which case this is huge. And we'll bypass this problem, or we will be able to cope with this problem in 2 steps. The first step that we'll now be talking about is generalizing our experts algorithm so that it does not only work with costs which are between 0 and 1, but which are between 0 and rho for some rho. This is kind of straightforward. Then our regret term gets a little worse, but that's okay. And then we'll still have to modify some things because in general these terms are unbounded, so there's no rho which can get us there. But the general spirit will be exactly like this. We will feed some fake sequence to our experts algorithm, which is correct in expectation. And the only thing that we'll have to make sure is that our experts algorithm is able to deal with these numbers that we're giving it. The first thing that we'd like to now do is just talk about algorithms for the experts problem where the costs are not between 0 and 1, but between 0 and rho. And that is surprisingly simple to deal with by just scaling everything to the respective interval, and then nicely things just cancel out. So let's see this. We have so far experts algorithms for this LIT somewhere between 0 and 1. And now we'll set LIT somewhere between 0 and rho. Now, is this difficult or not? It isn't. What you can do is you can feed LIT hat, I now want to call this, which is just 1 over rho times LIT to your experts algorithm. And if we now have the following property, if the expected cost of our algorithm on the hat sequence is at most alpha times the cost of the best action on that hat sequence plus beta, then what does this mean? This of course means that the expected cost of 1 over rho times the LIT without the hats is at most alpha times the minimum of the sum of the costs of the 1 over rho LIT without the hat. And what does happen now? Let's multiply here both of these sides with this inequality by rho. So what we're getting is the expected cost of our algorithm. If we are just now evaluating it on the LT sequence and not on the L hat T sequence, well, here on the right hand side, the first term, this now just cancels, and here this beta, this will be multiplied by rho. So in particular, if we were using multiplicative weights, then we could have, for example, alpha being 1, beta being 2 times square root of t times ln n. And this means now we get a new regret for the setting in which the rewards are between, or in which the costs are between 0 and rho. The regret will be at most 2 times rho times square root of t times ln n. Good. So this is super simple. Everything that is just a multiplicative scale just doesn't hurt us at all. Well, it does hurt us because, of course, this regret term that we have now gets multiplied by rho. But other than that, nothing changes. You could, by the way, in principle, also do something like this with additive shifts. And somehow this is the reason why you can also talk about rewards rather than costs, because also there you can play the same tricks. But that's not super important for us now, because what we actually want to talk about is this bandit feedback setting, where we get to know only the cost of the action that we've just chosen. And for that, we saw, okay, we had now defined this fake sequence for which we couldn't guarantee that the costs are between 0 and 1. Now, are they between 0 and rho? Not quite. So there's some, and not for any rho. So there's something more that we'll have to be talking about now. Good. So let's now come back to our idea, which turned out to almost work, but not quite, to set this LIT tilde to be LIT divided by PIT if this is the action that we're currently playing. Otherwise, we want to set it to 0. Now, can we choose a rho such that this LIT tilde will be always between 0 and rho? We cannot, because this PIT might be arbitrarily small, this might be maybe even 0, and in which case this term here, this ratio will just be unbounded. Therefore, we are now slightly changing the probabilities. Namely, what we're doing is we're adding a tiny bit of a uniform distribution to the probabilities, and this way we make sure that what we're getting here will be bounded. This LIT divided by PIT will turn out to be bounded. And the algorithm now looks as follows. So once again, the problem here is that this will not always be at most rho for any rho. And therefore the new algorithm is the following. In step T, we'll do the following. We will get a probability vector PT from an expert's algorithm. Then we will set Qt to be equal to 1 minus gamma times Pt plus gamma over n, and this I mean for all actions I. Now we will choose IT based on this probability distribution Qt. Importantly, those sum up to 1 just because the PIT sum up to 1, and this gamma over n, they sum out, or the 1 over n that we're adding, they are also summing up to 1. So this is important that they are summing up to 1 to make this step reasonable. And now we'll return exactly what we were planning back to the algorithm. Namely, we'll return some LIT tilde. Namely, we'll return LIT divided by QIT for I being equal to the action that we chose and 0 otherwise. This is what we return to the expert's algorithm. And this expert's algorithm, we should be aware, is running with a row of n over gamma. And why this n over gamma? Why does this work? We know that this LIT will always be at least 0, of course. And how big can such an LIT be? LIT tilde be? This will always be at most 1 divided by the respective QIT. And how big is a QIT at least? Any QIT will be at least gamma over n, so this will be at most n over gamma. So this is why this choice of row actually fits to this choice of LIT, because the LIT tilde, because all these LIT tilde are bounded by n over gamma. And our hope is now that this will work out. Now, it's not quite as obvious that this is what we want. Well, what we do see is that these LIT tilde, that their expectations are again the LIT. But is this enough for our algorithm to succeed? And how much does it hurt us that we're not doing what the expert's algorithm is telling us to do, but that we're introducing this some extra things here? Does this hurt us? Those are the things that we'll have to talk about. One thing that we should observe, though, is that this does feel somewhat meaningful. Namely, what we're doing here is actually introducing some kind of exploration. A full feedback algorithm doesn't need to choose actions which never turn out to be good so far, because it does observe when these actions suddenly become good. But this is now different, because we don't get any feedback for actions that we don't choose. It actually does make sense to once in a while choose an action which was actually not so good so far. And this is also some intuition that you might have here, that what we're doing here is not just following what the expert's algorithm is telling us to do, but with the probability gamma, we'll just choose one of the actions uniformly at random to just get an idea of what's going on. And the hope is that if we choose gamma small enough, then this does not actually hurt us. So if this gamma is small enough, hopefully this doesn't hurt us too much, and the only cost that we're facing is whatever the expert's algorithm is facing as the cost, while we still have to make sure that somehow that this is only correct, the feedback is only correct in expectation, that this does not hurt us. And this is exactly what we'll be now talking about more formally in the analysis of this algorithm, respectively this algorithmic approach. We now want to show that this black box transformation actually fulfills what we want it to be, namely that we can turn a no-regret algorithm for the full feedback setting into a no-regret algorithm for the bandit feedback setting, for the partial feedback setting, where we get to know only the cost of the action that we've just chosen and not the cost of the other actions. And to make this now not unnecessarily complicated, I'd like to talk about the multiplicative weights algorithm as the expert's algorithm, although in principle you could also do the same things for any other algorithm, but then you would, of course, the guarantee that you would be getting depends on the guarantee that holds for that other algorithm. And if we were now to prove this in a very general sense, things would just get much more messy than they have to be. So what we'll be showing is the following theorem. We will be showing that when using the multiplicative weights as the expert's algorithm, the Bandit algorithm guarantees that for any sequence of cost vectors L1 through L capital T, the expected cost that the algorithm incurs is at most 1 plus eta times the minimum of the best of the cost of action I, taking the minimum over all I, plus n times ln n divided by gamma times eta plus gamma times t. So what we'll see later is that this can also be turned into a no-regret algorithm by choosing gamma and eta appropriately. Gamma, I hope you recall, this is the probability that we choose a uniform distribution in any certain step. This is what we mixed into to get from our P to our Q. And so now we will have the same trade-off for eta and as we have for gamma, namely that we don't want it to be too big, because if it is too big, then either here or there, this will blow up, but if it is too small, then this term will blow up. Good, but let's defer these discussions until only after the proof. Let's see how we prove this claim. And in order to prove this, we now first fix any choice capital I1 through IT. What were these? These were the actions that are chosen by our algorithm. This fixes, of course, the sequence of the cost vectors, of these fake cost vectors that are fed to the experts algorithm, which we called L tilde. Now, what would multiplicative weights do on these L tilde vectors? The guarantee of multiplicative weights tells us that we get the following. Take the sum over all timestamps, take the sum over all actions. What's the probability that we choose the action in step t times this fake cost vectors entry for this action in step t? This is at most 1 plus eta times the minimum of whatever turns out to be the best action with respect to these fake cost vectors, plus rho times ln n over eta. And how big was rho? Let's plug that in. Rho was equal to gamma over n, no, n over gamma, so this is n times ln n over gamma times eta. Good, so this, now when we're fixing what the algorithm does, this is what is true for the p and the L tilde vectors that we'll be coming across. Of course, here we also have a tilde because so far we're only talking about the L tildes. There's nothing actually talking about the actual L's here. And we're also not yet bounding the cost that our algorithm incurs. Because our algorithm isn't actually using these PTs, it is using the QTs. So how are these QT defined? These QT are equal to 1 minus gamma times the PT plus gamma over n. So what do we know now? If we were to take the sum over the QIT times LIT tilde, well, that's just something that we can write out. Namely, it's 1 minus gamma times this sum over the PIT plus gamma over n, and then we'll have exactly the same kind of a sequence, the same kind of a sum, where we're only talking about now the LIT tilde. And what can we bound? How can we bound this? Well, we can apply, of course, this bound here now on this term, which tells us that this entire sum here is now at most, well, one thing we can use is that this here is, of course, at most 1, and here we can use the bound that we have from above. So what is it that we're getting here? We're getting at most 1 plus eta times the minimum of all these LIT tilde in the sum plus n times ln n over gamma times eta plus, and then we'll just copy this last term as before. Good. So what have we done so far? We are just only talking about what happens during one execution of the algorithm. So keep all randomization fixed, and let's just talk about what is it that the L tilde vectors, the Q vectors, the P vectors look like. And for these, we always have, for example, that this inequality is fulfilled, namely that the sum of the QIT times LIT tilde fulfill this inequality. This is being derived from the guarantee of the multiplicative weights algorithm. But what we've not yet taken into consideration is that these LIT tilde, they are actually random variables. So this is only, actually everything here is a random variable. Also the QIT is a random variable. And what we'll actually want to do eventually is take the expectation around everything. Because then what we want to understand is what is the actual expected cost of our algorithm. Good, so let's take the expectation on both sides. We'll be getting that the expectation of what we have here on the left-hand side is at most the expectation of what we have on the right-hand side And now, of course, we can use linearity of expectation. So what are random variables in here? Maybe let's be clear. These LIT tilde, those are random variables, and also the QIT. Those are random variables because the QIT depend on the probabilities that we chose, or those are probabilities, but they depend on which actions we chose in previous iterations. And the LIT tilde, of course, they also depend on which action we chose, we choose in the current iteration. But the rest, those aren't random variables here. So this 1 plus eta, this is not a random variable, or this is not a random variable. Here, of course, we again have a random variable. So let's see where we are getting. Apply linearity of expectation here. Now we get an expectation of QIT times LIT tilde. Okay, this is something we'll have to be having a closer look at. This 1 minus this, eta, this is just some constant. Then we have here an expectation of a minimum. This is what we need to have a closer look at. This is not a random variable. This isn't random either. But here, this is again a random variable. Good. So 3 expectations we'll have to talk about. Now, the first thing I'd like to do is I'd like to see here, this is at most the minimum of the expectation of that sum, because the expectation of a minimum is always at most the minimum of the expectation. So we can move the expectation inside there. Now we actually only have 2 kinds of terms here. Namely, we'll have this expectation of some LIT tilde, and then we'll also have the expectation of the QIT times LIT tilde. But let's first talk about these expectations. How big are they? Well, how was LIT tilde defined? LIT tilde was defined to be LIT divided by QIT. But all of these are random variables now. Okay, but only QIT if this is the action that we're choosing in this particular step. So what makes it complicated, for at least for me, to think about this LIT tilde is that this is a random variable which does not only depend on what we're doing in the current step, but also in the previous steps, because all the probabilities of actions in the current step, depending on what we observed in the previous steps, this again depends on what we did in the previous steps, and so on. But fortunately enough, this does not matter too much here. Namely, to now bound this expectation, or to understand this expectation, what we can do is we can fix that in the first step we'll choose action I1. In the second step we'll choose action small I2, and so on. And we'll do this for the first t-1 steps. Now this fixes the qt vector, because the probability that we choose an action in a step t, this is a random variable itself, but it only depends on which actions we chose earlier. And what we now have is that the probability that in step t we choose action I conditional on this choice of I1 through IT, or IT-1 to be precise, this is exactly QIT. And this now means that the expectation of LIT tilde conditional on these other choices this is QIT times LIT divided by QIT, so this is exactly what we want it to be. But this is only for a conditional expectation, namely if we now fixed what happens up to step t minus 1. But unfortunately, this holds for any choice of I1 through IT minus 1. And this tells us that the expectation of LIT tilde, unconditional, this is, we can write as follows. Take the sum over all possible choices for I1, all possible choices for I2, and so on. Now, what's the probability that we are choosing exactly these actions and then times the conditional expectation that we were talking about here? Now, this conditional expectation, regardless of what these small i's are, will have always that this is at least that this is exactly LIT, and the sum of all these will be exactly equal to 1. So this is why also this unconditional expectation will be equal to LIT. Good. So where were we? We now know some things, namely, let me add this maybe in green, this here we know is LIT. And also this thing here is equal to LIT. So this helps us to upper bound all of this by n times t, because each of the LITs is at most 1. Good. Now what we'll still have to talk about is this weird thing here, the expectation of QIT times LIT tilde. What's the expectation of QIT times LIT tilde? We'll do the same argument. Now I think it's even a little more complicated, or maybe if this up here felt too trivial for you, now I think it makes even more sense to do it this carefully, because we'll have to be realizing that what we're doing actually is correct. So again, we fix I1 through IT arbitrarily, or IT minus 1, I mean. And let's call them again I1, small I1 through IT minus 1. So this now means that this QIT is also fixed. And so we can now say this conditional expectation we fixed everything as we wanted to fix it. You know, this isn't actually a random variable. So we can just move this out and then write the expectation only over this L tilde. Now, this is something that we already know, namely, this is what we have here. So, this expectation is exactly equal to Li tilde. And now, by the same argument, we now have that the expectation of Qit times Lit tilde, so the unconditional expectation, this is nothing but the expectation of Qit times Lit but now here this Lit, this is not a random variable. This is what the adversary fixes in advance. So now we can move this outside the expectation. And we only have here the expectation over Qit. And what's the expectation over Qit? This is Qit, this is the probability that we choose action I in step t. So we can also write this just as the probability that we choose action I in step t. Good. Now, this helps us also to further understand what we had up here. Namely, we can now also talk about this quantity here. And we can see, okay, this is exactly the probability that we choose action I in step t times Lit. Fantastic. Now, how big is this here on the left-hand side? This is actually nothing but the expectation of the sum over all time steps L capital IT in step t, just by definition of the expectation. Fantastic, because this is exactly the expected cost of our algorithm. And now we'll have some other things here on the right-hand side. And this is exactly what we wanted it to be, because we wanted to show that the expected cost of our algorithm is at most 1 plus eta times the minimum of all the Lit plus n times ln n over gamma times eta plus gamma times t. So here also the n cancels and we only get gamma times t. So this indeed all together proves our claim. Good. So how does this proof work? It is actually nothing but our very first thought that we wanted to make sure that these Lit tilde are an unbiased estimate of the Lit. And somehow this turned out to be indeed correct. This is what we have here. And the expectation of Lit tilde is nothing but Lit. And also, here this was a little more complicated to talk about, but eventually it is exactly what we want it to be. Namely, it is the probability that we choose action I in step t times Lit. Good. And after we have these things, then all we actually do is we combine this with the guarantee of multiplicative weights. This was the guarantee of multiplicative weights, or well, what we started from. Then we rewrote this a bit in terms of the queues so that this is actually already taking into consideration that we are having also this exploration part in which we choose one of the actions uniformly at random with probability gamma. So this is where actually this part here is coming from. But then just linearity of expectation is doing the trick. And this to me is actually quite crucial, because if you wanted to just analyze this entire random process, this would feel super complicated because there are so many dependencies happening here. But given that we can apply linearity of expectation, this helps us to disentangle what we have in step t, or the randomization that is happening in step t, from what is happening in steps 1 through t-1. So to some extent, the magic of this proof also lies in this linearity of expectation, that we can take things apart and then put things together again. As I was saying, for me at least, this whole random process that is taking place here feels extremely complicated. But, and this is I think one thing that I hope you've learned by now, that linearity of expectation is a super useful tool, just because all these correlations between different time steps, for example, or between different actions, they don't matter for the expectation. Cool. So what does this bound now mean? Let's maybe again write this down, the bound that we have. So the expected cost that our algorithm incurs. This is at most 1 plus eta times the cost of the best action plus n times ln n over gamma times eta plus gamma times t. Now what's the best choice of gamma? What is the best choice of eta that you can do here? Well, you could now try to minimize this and you would get something. I'm now not doing the exact minimum, but it is certainly very close. Namely, what you can do is you can set this gamma and this eta both to the third root of n times ln n over t. And what do we get now? Then the expected cost of our algorithm will be no more than the cost of the best action plus, and now what do we have? We have eta times t plus n times ln n over gamma times eta plus gamma times t. And how big are these things? This and this will be the same, namely both of them will be n times ln n to the power of 1/3 times t to the power of 2/3. This is what we're getting out of this, because here the t cancels and this is the same thing. Now what do we get from this? It is also the same thing, because here we're getting gamma times eta, so this will be the square of this, and now also things cancel the same way, so we'll get 3 times this much. Which, by the way, tells us that our regret will be no more than 3 times n times ln n to the 1/3 times t to the 2/3. Cool. So we have a no regret algorithm because this grows sublinearly in t. And this is in a weaker model, so where our algorithm is actually gets less feedback. It only gets to know the cost of the action that it chose, not of the actions that it did not choose. Yet still we are able to get this kind of regret. But is this the best that we can hope for? What did we have for the full feedback setting? There we had something like square root t times log n. Now here, n we should always think of as being smaller than t, so what really is important is how does this grow in t. And now we have t to the 2/3. That's not as great as a square root of t. And as a matter of fact, the best bound that one can achieve here in this setting is not t to the 2/3, but it is actually square root t. And this is exactly what we will be doing next time. We will be showing that we can modify this slightly and then get a regret bound of something in terms of n times square root t rather than t to the 2/3. How will we do this? Well, we will then have to have a closer look at the analysis of multiplicative weights again. There we'll have to change a tiny bit, and then we'll just have to go once again through this analysis that we did today, and then things just mix really nicely to then get this improved bound. This is what we're doing next time. I hope you enjoyed today's lecture. Please, as usual, do let me know if you have any questions. See you next time. Stay safe. Bye.